We have told you our final exam will be next week, the same day, same time, the same place. So there will be June 17th, 3 p.m. here, 310. Room 10. So you need to bring your laptop, and then in that laptop you have to install all the software and license. Otherwise, you cannot solve the problem. And as I told you, for your final exam, I will use your assignment. So if you if you submit your assignment by yourself, in a proper way, then you will not have any problem to solve your final exam. But the thing is that your 3 times of the assignment has not been solved by myself, so you don't know what the answer is. Okay? So as I promised to you, I will leave you your 3 times of the assignment one by one. So that would be helpful for you to prepare the final exam. Okay? So if I remember, we have the first assignment, which is this is your first exam. At the time we have used WatchBest. Okay? So this WatchBest is without the proper license, you cannot solve this side of the problem, because here we have the a lot of variables, decision variables, and a lot of constraints. So I will use this problem. Of course, I will change it some number, so you need to solve the problem again. Although you now have seen the answer here for your assignment, that's not the same as your final exam. Okay, you understand? So the first problem, and then here, the first problem was the PMP problem. So if this company wanted to set up 4 warehouses for 11 cities, which cities should be selected, minimizing population weighted average distance. This is a typical PMP problem. So P median problem. So if you want to solve out, then you need to map out all the necessary variables here. So here decision variables will be 11 by 11 matrix that satisfy from which facility to which demand side. And then also you need to have another matrix that decides which city should be selected as a service center, isn't it? And then the thing is that the objective function here is the one that you have to multiply with the distance and then the population. So this is PMP problem. Okay, and also in the PMP problem, you already set up the number of the service center, distribution center. So in this case, there is 4. So if you run this out, then you get the answer. Okay. And also some of you asked me, my answer, my decision variable is a little bit different than yours. That is also okay, as objective function is the same as mean. So in this case, the objective function here is the weighted average distance from the service center and each customer side is 3.14. Okay, that is quite natural for this type of meaning problem. Okay. And the next question is just a little bit divisions of the previous problem. So that is the capacitative problem set. So everything is the same, but only we apply the capacity of the facility individually. So we're gonna have the same conditions except this capacity conditions. So each single capacity cannot treat the volume more than 32,000. So that was the thing here. And we just solve it, then we get the answer here. Okay. So I said, although I had the answer CT 4, 8, 9, 10, it's okay as long as the cost is the same as 1,316,540. Okay. And the third question is the number things. That is LSCP. So we relax the conditions of the number of the facility. So we wanted to minimize the number of the facility. So in this case, its objective function is the number of the facility. But on the other hand, we apply the quality constraint and limit the distance between service center and the city under 30 kilometers. So only the cases that comply with this service constraint can be the answer. So we use another matrix here. Then out. So the minimum facility to satisfy this service constraint condition is the 3 facility. You need at least 3 facility, and then the 3 facility can be here. And then the first question is another revisions of this. So they wanted to maximize the coverage of the warehouse. Because the former answers, 3 facility is unrealistic for them, but they wanted to maximize the coverage of the services by setting up these 2 service centers. In this case, we use the first question is MCLP. MCLP indicates we reduce the number of the facility by 2.
serviced population. Serviced population can be here calculated from serviced population. So serviced population is the population of that city multiplied with the city itself. Then we can so maximum coverage of this setting 98%. With the city 2 and 11, you might have the different two city, but it's okay, it's accepted as long as the ratio is same as 98.6%. And here we can make up also capacity condition over this problem set, that is CMCL problem setting. So all the facility is applicable with the maximum capacity of the 40,000. Then using that one. Yeah, 77%. 77.7%. Because we applied additional condition over the problem of the poor, so coverage has been reduced from 98 to 77%. And then later, this company handed over this project to the government, which is concerning about equity of the service throughout the cities. So that means we need to apply the different objective function in system. So then maximum distance between city and facility should be minimized. So it is minimax. So minimize the worst case scenario. That is the new objective function here. So if you apply that one, you can also get same condition here. And to set up your objective function, you first have to calculate the worst case scenario. And then you need to minimize that worst case scenario, isn't it? So you need to first calculate what is the maximum. What is the maximum? So what is the distance? What is the maximum distance? And then you need to use that one to minimize. Okay? So this is second order optimization function. Use this one. Okay. So maximum, minimize the maximum distance between source point and then customer side is the 34.6 in this case. And also they wanted to apply the capacity constraint here. So that is CP. In addition to the previous problem, you just set up. This is extra condition here. And then again, after you apply the capacity conditions, capacity constraint additionally, your worst case scenario has been worst. So the longer maximum distance can be found out throughout these conditions. So, okay, and then up to here is the what's best optimization problem. And from the problem 8 through 10, it is about the warehouse layout optimization. You remember the questions here. In my slide, I induced how we get the optimal depth of the block stacking, because the block stacking suffer from the inefficiency issues. Firstly, they wanted to calculate what is the total floor space. It is not the space that covered by the product, but it is floor space. So how many floor spaces is used while you use lane depth of X9. So here, lane depth of X9 is not the optimal conditions. This is the given conditions. So after we check out, calculate the baseline, then we start to optimize the lane depth. Then we get the space saving, isn't it? So that is the natural order. So we firstly want to know currently if you use the given conditions, which is X9, then how many floor spaces is used. So that is the one that I firstly asked throughout the question 8. So we can calculate this out. Here. This is the table that I used. And then, firstly, you need to calculate how many Ys. Ys means how many columns in the bulk plane. How many bulk plane should be used while it is maximum. But so how many depths? Here, this is the first one that I wanted to calculate. So that is the total number of the pallet should be divided by the lane depth, which is 9, multiplied by stackability. So by one lane, you can consume, you can digest 18 pallet, isn't it? So if you divide 5,000 by 18 pallet, that is number of the lane that you can use in maximum, isn't it? But the thing is that 5,000 is not, it's arrived at once, but it is the consumed, reduced by customer's order, so you need to calculate time averaged Y. So that is the here at time. So is eta. This one. So this is the time averaged number of block stacking lane. So that is the calculate throughout this condition. So I already explained how we induce this formula, and then only things that you can do by calculating eta is the applying this condition. You need to know what is y. So y is already calculated. You know what is q, x, y, z, and z, y by 2. So that is the formula that you have to use. So after you calculate eta, then you can use this one over here, isn't it? And then you know what is W and C. That is already here. Isn't it? C and then W here. Isn't it? So, and then you know what is X, L. So to answer for the question here, this is the calculations of eta, and this is the calculations of the W plus C, and this is the calculations of X, L, and plus part A, part of the corridor width. And then answer is the multiplication of the three parts. So that is the original space that before optimization. But what you need to improve here is the find out the optimal index, optimal x. Okay, and then I also inform you how to calculate optimal x. So if you make a derivative over storage here, this storage. After you apply this condition here, then you get the x. So this is optimal. This is optimal index. Okay, and then I ask what is optimal index. So just apply this formula, then you can find out optimal x is 29.7. It is number of the pallet as a depth. So you use 30. So you have to find out the bulk lane that can be occupied by 30 pallet. So this is 30 pallet. So then you have the new x, isn't it? Instead of the old x, which is 9. So then you can recalculate the space after you apply the new x. So that is the here you again calculate eta by using x30 instead of x9, and this is the same. W plus C is the same, and then XL plus half of A is different because you have a new X. Then this is a new space. So new space is smaller than the older space, isn't it? But the gap between two spaces is the space saving after you optimize the lane depth in block stacking. Isn't it? So this is the question from 8 to 9. Okay. And second assignment was the